Welcome back to G Fun Facts Online. Today, we are diving deep into a paradox of thermodynamics that affects every single one of us. As our planet warms, our demand for cooling accelerates. By the year 2050, the global demand for air conditioning is expected to triple. But here is the problem. The very technology we use to cool ourselves, vapor compression refrigeration, is actively contributing to the heat. It is a century-old cycle trapped in a dangerous feedback loop. We burn fossil fuels to power compressors that pump refrigerant gases. If those gases leak, they possess a global warming potential thousands of times higher than carbon dioxide. For decades, material scientists have been hunting for a solid-state alternative. They wanted a way to pump heat without fluids, without compressors, and without volatile gases. They looked at magnets and electric fields, but the solution might actually lie in something far more visceral: mechanical force. This is the story of elastocaloric cooling. It is a technology that mimics the mechanics of a muscle and the physics of a steam engine, all trapped inside a lattice of superelastic metal. By simply stretching or squashing a piece of metal, we can generate intense cold. It promises a future where our air conditioners are made not of pipes and pumps, but of shape-shifting alloys that breathe heat in and out. Today, we are going to explore how metal muscles are poised to replace Freon, the physics that makes it possible, and the engineering race to build the first solid-state fridge. To understand how a solid metal can cool a room, we first have to abandon our intuitive understanding of metals as rigid, static objects. In the world of shape memory alloys, or SMAs, metal is a dynamic, living crystal. This phenomenon is called the elastocaloric effect. It is a thermodynamic event where a material shows a significant change in temperature under the application or removal of mechanical stress. Unlike the gas in your current AC, which cools when it expands, these metals cool when they are allowed to relax. The process works in a cycle. First, there is the loading phase. You take a piece of elastocaloric metal, like a wire or a cylinder, and you stretch or compress it. This mechanical work forces the internal crystal lattice to reorganize. This reorganization releases energy in the form of heat. The metal instantly becomes hot. Next, you have heat rejection. You let that heat dissipate into the environment or a heat sink, all while keeping the metal under stress. The metal returns to room temperature, but it is still loaded. Then comes the unloading phase. You release the stress. The crystal lattice snaps back to its original state. To do this, the lattice must absorb energy, or entropy, from its own atomic vibrations. The result is that the metal's temperature plummets instantly. Finally, this cold metal is exposed to the air or fluid you want to cool, absorbing heat and completing the cycle. The magic here happens at the atomic level, in a reversible phase transformation between two crystal structures, austenite and martensite. Austenite is the high-temperature phase. Think of this as the relaxed state. The atomic structure is highly symmetric, usually cubic and stable. In this state, the atoms have more freedom to vibrate, meaning the material has high entropy or disorder. Then there is martensite, the low-temperature or stressed phase. When you stress the metal, you force the atoms to shear and align into a less symmetric, more ordered structure. Because this state is more ordered, meaning lower entropy, the excess energy must go somewhere. It is ejected as latent heat. When you release the stress, the material wants to return to the high-entropy austenite phase. It sucks thermal energy from its surroundings to fuel this atomic reshuffling, creating a cooling effect. This is the latent heat of transformation, the solid-state equivalent of boiling and condensing a liquid refrigerant. Now, not all metals can do this. If you stretch a steel bar, it heats up slightly due to thermoelasticity, but the effect is negligible. Elastocaloric cooling requires superelasticity, the ability to undergo massive reversible strain, up to 10%, without permanent deformation. The gold standard for this is nickel titanium, also known as Nitinol. Nitinol alloys can achieve an adiabatic temperature change of up to 30 degrees Celsius in a single cycle. This is massive. It creates a temperature lift sufficient for refrigeration and air conditioning. Originally discovered by the Naval Ordnance Laboratory, Nitinol was famous for being indestructible spectacle frames. Now, it is the heart of the cooling revolution. However, titanium is difficult to process, and nickel is expensive. Furthermore, standard Nitinol has a functional fatigue limit. Eventually, the crystal structure forgets its shape, if not engineered perfectly. For mass adoption, we need cheaper materials. Copper-based shape memory alloys, specifically copper zinc aluminum or copper aluminum manganese, are the budget-friendly contenders. They use much cheaper raw materials and are easier to machine than Nitinol. Some single-crystal copper alloys demonstrate huge latent heat capacities. The downside is that they are generally more brittle. While Nitinol can withstand millions of cycles of squashing, copper alloys tend to crack sooner. However, recent advances in adding elements like manganese and using single crystal growth techniques have improved their durability significantly. The most exciting development in the last year or two is the marriage of additive manufacturing or 3D printing and elastocalorics. In the past, we were limited to wires and tubes. Now, researchers at places like the University of Maryland and the Fraunhofer Institute are printing intricate honeycomb and lattice structures out of Nitinol powder. Why lattices? They maximize the surface area to volume ratio. A solid block of Nitinol would take too long to transfer its heat to the air. A microlattice allows air or water to flow through the metal sponge, exchanging heat instantly. This solves the heat transfer bottleneck that plagued early prototypes. Knowing the physics is one thing, but building a machine is another. How do you design a fridge that needs to stretch metal thousands of times a day? A vapor compression fridge uses a compressor to move gas. An elastocaloric fridge needs a driver to move metal. This is the primary engineering challenge, designing an efficient mechanical actuator. Early designs stretched wires using tension. However, wires can snap, and fatigue cracks grow quickly under tension. The industry has shifted toward compression. Squashing a Nitinol tube or cylinder is much safer. If a crack forms, the compressive force keeps it closed rather than tearing it open. Designers use cam drives, hydraulic pistons, or piezoelectric motors to apply the force. To maintain high efficiency, the system must employ work recovery. When one piece of metal expands or unloads, it releases mechanical energy. A smart system uses that release to help compress the next piece of metal, recycling the mechanical work just as a hybrid car regenerates braking energy. To get a temperature drop of 20 degrees, you can use a single cycle. But to freeze food at -20 degrees in a 30-degree room, you need active regeneration. Imagine a fluid, usually water, or a glycol mix, pumping back and forth through the elastocaloric metal structure. The fluid flows right as the metal heats up, rejecting heat. Then, the fluid flows left as the metal cools down, absorbing heat. This establishes a temperature gradient along the length of the metal. The left side gets colder and colder, while the right side stays hot. This thermal ladder allows elastocaloric systems to achieve temperature spans far greater than the capability of a single piece of wire. Recent prototypes have shattered records, achieving lifts of over 75 Kelvin using multi-stage cascade architectures. Why go through the trouble of reinventing the fridge? The answer lies in two metrics: the coefficient of performance, or COP, and the global warming potential, or GWP. Vapor compression is mature. It has been optimized for 100 years, yet it is hitting a theoretical wall. Theoretical studies suggest elastocaloric materials can achieve 60 to 80% of the Carnot limit, which is the maximum theoretical efficiency allowed by physics. Traditional AC units typically operate at only 40 to 50% of this limit. The reason is that the phase transition in solids involves very little entropy loss compared to gas compression. It is a more ordered way to move heat. The most compelling argument, however, is environmental. Current refrigerants, like R410A, are better than the old Freon, but they are still potent greenhouse gases. A typical AC leak contributes as much to global warming as driving a car for months. The elastocaloric refrigerant is a piece of metal. It has a GWP of 0. It cannot leak. It is fully recyclable. If a Nitinol core breaks, you melt it down and recast it. For years, the skepticism surrounding elastocalorics could be summed up in one question: won't the metal break if you bend it millions of times? In standard metallurgy, metal fatigue is the enemy. However, Nitinol is unique. It is designed to phase transform. In a landmark study around 2023, researchers demonstrated ultra-high fatigue life in Nitinol cylinders. By operating under partial transformation modes and optimizing the microstructure grain size, they achieved over 70 million cycles with negligible degradation. A domestic fridge cycles roughly 20,000 times a year. 70 million cycles represents centuries of operation. The fatigue problem is rapidly moving from a showstopper to a solved engineering constraint. Another issue is hysteresis. This is the thermal friction of the phase change. When you load and unload the material, the stress-strain curve creates a loop. The area inside that loop represents lost energy. The solution has been developing narrow hysteresis alloys. By doping Nitinol with copper, cobalt, or iron, material scientists have created slim loop alloys that require less force to activate and waste less energy, drastically boosting the COP. The field is moving fast. Researchers at the Hong Kong University of Science and Technology recently unveiled a multi-material cascade elastocaloric cooling device. By using different alloys optimized for different temperature ranges and stacking them, they achieved a record-breaking temperature lift of 75 Kelvin. This proved that solid-state cooling isn't just for mild air conditioning. It can handle deep freezing. Meanwhile, the University of Maryland has moved beyond lab bench curiosities to functional systems. They demonstrated a system delivering 260 watts of cooling power, comparable to a small compact refrigerator, using compact bundles of Nitinol tubes. This was a critical proof of concept that elastocalorics can scale up. In 2024, the World Economic Forum named elastocalorics one of the top 10 emerging technologies. This recognition signals a shift in funding and commercial interest. We are seeing the transition from pure academic research to startup incubation. So when will you buy an Elastocaloric AC? Don't expect the whole house unit immediately. The technology will likely appear first in niche markets, where efficiency and compactness outweigh cost. Electric vehicles are a prime candidate. Range anxiety is real, and current heating and cooling systems drain the battery significantly. Elastocaloric heat pumps are more efficient and compact, potentially extending EV range by 5 to 10%. Space and defense sectors are also interested because these systems work in zero gravity and are rugged. Eventually, as regulatory pressure like the EU's F-gas regulation forces a move away from HFCs, we will see a retrofit of the HVAC industry. Major manufacturers like Haier, Gree, and Daikin are monitoring this closely. We are currently bridging the gap between a working university prototype and a mass-manufactured product. We are standing on the brink of a thermal revolution. For a century, we have relied on the compression of gases, a brute force, chemically hazardous method, to keep our civilization cool. Elastocaloric cooling represents a return to the elegance of solid mechanics. By harnessing the atomic memory of metals, we can build refrigerators that are silent, refrigerant-free, and hyper-efficient. The metal muscles of Nitinol and its cousins are strong enough to carry the weight of our cooling demands. While engineering challenges in actuation and cost remain, the physics is sound, and the prototypes are proving the skeptics wrong. The question is no longer if solid-state cooling will happen, but how soon it will render the hiss of the Freon compressor a sound of the past. Thanks for listening to G Fun Facts Online.